This is a counting circuit. This is the breadboard orientation, and this is the PCB orientation. Both the breadboard orientation was designed by me, and the PCB orientation was designed by a former ACES student. Now, the point of a counting circuit is to count 0 through 9 and up and down. So, to give a demonstration, I will take my 9-volt battery and my breadboard orientated version of a counting circuit and demonstrate. This is the fastest it can count at, and now this is a normal speed. And as you can see, this is counting down, but if I flip this switch, it will start to count upward. This circuit is made out of many components, starting from the NAND gate oscillator all the way to the 7-segment display. Each of them plays a key role in the counting circuit, and without any of them, it would not function at all. I will go into more in depth on each component, starting with the NAND gate oscillator. This is a diagram of the NAND gate oscillator, the beginning of the NAND gate oscillator, that is. You can see a 10K ohm resistor leading to pin 12 and pin 13 of the IC, leading also to a button input leading to ground. On pin 11 of the IC, it leads to the negative end of an LED, with the positive end of the LED connecting to positive ground. Now, this is just the beginning of the NAND gate oscillator. As seen here is the full NAND gate oscillator, which the objective is to output a clock signal, which is a signal that is constantly at a high and low oscillation. And this is the power that powers the counting. Without it, you would have to manually change the numbers, but because there is a clock signal, the numbers change by the high and low input or output of the NAND gate oscillator. Next up, the 3 other main ICs in the circuit. A 4017 IC, as seen here, can be used in a counting circuit as a decade counter. A decade counter is a type of digital circuit that counts in decimal digits 0 to 9 rather than binary digits 0 to 1. When an input pulse is applied to the clock input of the 4017 IC, it increments its internal count by 1 and produces a corresponding output on one of its 10 output pins. For example, if the input pulse is applied while the external count is at 0, the output on the pin 3 will go high, indicating a count of 1. The next input pulse will cause the output pin 2 to go high, indicating a count of 2, and so on. A 4510 IC is a BCD, also known as binary coded decimal counter, which is a type of digital circuit that counts in decimal digits 0 to 9 by converting the binary count internally to BCD. When an input pulse is applied to the clock input of the 4510 IC, it increments its internal BCD count by 1 and produces a corresponding output on its 4 output pins. For example, if the input pulse is applied while the internal count is at 0, the output on pins 2, 3, 4 will be 0, 0, 1, indicating a count of 1 in BCD. The next input pulse will cause the output on pins 2, 3, 4 to be 0, 1, 0, indicating a count of 2 in BCD, and so on. Like the 4017 IC, it is also possible to reset the counter by connecting the reset pin to a low signal. This will set the count back to 0, and the first output pins will give the BCD representation of 0. The 4511 IC is a BCD to 7-segment decoder driver. It can take a BCD input and convert it to a 7-segment display format, which can be used to display decimal digits on a 7-segment LED or LCD display. In this case, we are using it for an LED display. The 4511 IC has 4 BCD inputs, a latch pin, and 4 7 output pins that correspond to the segments of a 7-segment display. When a BCD input is applied to the input pins and the latch pin is activated, the IC will convert the BCD input to the corresponding 7-segment code and output it on the segment pins. For example, if the BCD input is 1001, 9 in decimal, the output on the signal pins will be 1001, 1101, which will light up the segments needed to display the number 9 on a 7-segment display. This is the 7-segment display. The 7-segment display gets its input from the 4511 IC explained in the last section of the video. In the 4511 IC, each output pin corresponds to a letter, and each letter has its own pin on the 7-segment display input as seen on the diagram above. Now, the 4511 will output these in combinations, and when these combinations are correct, they will be perceived as readable decimal numbers. And that brings us here. This, as I mentioned in the first section of the video, is the PCB version of a counting circuit. This is the 7-segment display. Here are the 3 ICs that we talked about, and this is the NAND gate oscillator. All of this comes together as a proper counting circuit. Now you can see here, this is counting down, and if I flip the switch, this is now counting up. Thank you, and here for scale is the breadboard version of the circuit.